Hi, Tesserize here, and today I'm going to show you the Green's function of this operator, this differential operator. So why do I want to do this? Let's take a look. So once again, going back to the textbook Quantum Field Theory for the Gifted Amateur, we're finding the Green's function of this Laplacian, and this has applications in electromagnetism. So you see that the Green's function, they said the Green's function of this Laplacian is this, and it gives this. So in this video we're going to find out how we can solve this by ourselves using Fourier analysis. So the next video will focus on the second part, but in this video we'll talk about the first part. So namely, we want to in the book they wrote this particular statement, and then they say the Green's functions are given by this, and in this video we generalize. So we first let this quantity here be R, so we let this quantity here be R vector, and then we want to generalize to a more general differential operator, Laplacian minus a squared. And you see that in order to recover the original, the one from the textbook, we just set a equals to 0 and we obtain back the result. So the part highlighted in green here is the objective of our video, and today we will show how to show this using Fourier transform. So how do we start off? Alright, so the first step is to write the right hand side in terms of Fourier expansion. So okay, one important thing to note here is that you see the left hand side is a function. We have a function, a three-dimensional function, and we have a differential operator acted on this three-dimensional function. And on the right hand side we have a distribution. So this is a distribution. And what is a distribution? I think Brightside Mathematics has a great series on this. A distribution is basically not a function, but is a map from test functions. It's a map. So a distribution, I'll just say D. Okay, D is a bad idea, but let's say D is a distribution, and D is a map from from test functions onto some real number, and the real number is given by the integral of this function with the distribution dx. So briefly speaking, the distribution is you can put it into an integral and you get a real number. So we will be avoiding the mathematical formalism of distributions by working in momentum space and using Fourier transforms. So we are hiding behind the mathematical rigor, and we are going to by using Fourier analysis. So what is the right hand side? The right hand side is given by, this one can be quoted from any textbook, e to the power of I k dot r. So k is a vector, r is a vector. This is a three-dimensional integral. Okay, and what is the left hand side? So let this function first be g. Okay, so we want to show that and let's let g. So the right hand side is this, and the left hand side, let g equals to integral d3k over 2 pi cube. It's a Fourier transform with some sort of coefficients, e to the power of I k r. So this is a general form of g. So we want to find what g is to satisfy this equation. So let's go ahead and compute Laplacian minus a squared of g, and that is equals to integral g of k, and then we have minus k squared minus a squared, right, e to the power minus I k dot r. Okay, so what do we see over here? We see that if we want this to be equals to the right hand side, if we want this to be equals to, so the left hand side, this is the left hand side, and if we want it to equals to the right hand side, then we have to have this, we substitute it back in here. So if d3k over 2 pi cube e to the power of I k dot r. So what do we notice? We notice that we need this part and this part to be the same. So in other words, gk minus k squared minus a squared equals to 1, and g of k equals to minus 1 over k squared plus a squared. Alright, so now we have a Fourier expansion of the Green's function. So the Green's function is equals to integral of d3k over 2 pi cubed, and this is e to the power of I k dot r over k squared plus a squared. Right. Sorry. Okay. Okay, I might have missed a minus sign somewhere. But it's okay. We'll handle that later. I think there's supposed to be a minus sign here. Yeah. Okay. So sorry. I think I missed a minus sign. So let me just introduce it here. So this should be minus. So then this will be minus 1, and this will be minus, and then this will be minus 1, this will be plus, and this will be plus. Okay, so we show that this, so now we want to show that the Green's function, which is this in the integral form, should, so this is should equal to e to the power minus ar over 4 pi r. So how do we show now? So now the problem reduces to showing this relation. How do we show this? So that will be the focus of this video. Okay, so how do we go about showing that? Yeah, so the first step is to notice that this left hand side integral is spherically symmetric, right? So if you see, if we expanded it in terms of k in x, y, and z, right? If we express k in terms of x, y, and z, that wouldn't get us very far, because we have square roots to deal with in the bottom, we have poles. The first integral can be done using contour integration, but after that you run into problems because it's almost impossible. So what instead is we express k in terms of polar coordinates. So k equals to k naught sine theta cosine phi, sine theta sine phi, and cosine theta, where k naught equals to the magnitude of this k vector, and the r vector lies, and the r vector equals to, and the r vector, and basically the theta is the angle between k and r, such that k dot r equals to k naught r cosine theta. So yeah, so we have chosen one particular coordinate system that is pretty smart, that aligns with this r vector, so the exponent is simple, and in so doing we can start doing our integration. So first thing we know is d3k is equals to k naught squared sine theta d theta d phi dk naught. This is just the differential volume element in in spherical coordinates. So yeah, so let's go ahead and convert this integral. So our integral g of r equals to, let's pull out the 1 over 2 pi cube outside, integral of e to the power of I k naught magnitude of r cosine theta plus over k naught squared plus a squared, and then we have here we have k naught squared sine theta d theta d phi dk naught. And yeah, so do note that this variable we're integrating is from 0 to pi. This variable is 0 to 2 pi, and this one is 0 to infinity, as with polar coordinates. So we see the first obvious one to do is just the phi integral, which just gives us a factor of 2 pi. So this becomes 2 pi squared in terms of instead of 2 pi cubed. Then the next obvious integral to do is the theta integral. So okay, maybe I write it out more clearly first. We shall do the k0 integral last, and then next obvious integral to do is the 0 to pi e to the power of I k0 r cosine theta k0 squared plus a squared, and then there's a sine theta here. So yeah, d theta. Yes. So let's do the d theta integral. So it's just this. So you see it's very nice in the exponent. That's why we chose theta to be the angle between r and k0. So it's quite a smart choice. So we do this. So okay, then we have this k0 squared. Okay, actually I can pull out this k0 squared plus a squared e to the power of I k0 r cosine theta minus, and this is going to be I k0 r, and this is between theta equals to pi and theta equals to 0, right? Yes. And okay, so this is equals to, we can pull out some constants, so we just pull it out all over here, 2 pi squared r, and then minus 1 over I is I, so we have I over here. Then we have the 0 to theta, 0 to infinity, I mean, d k0 over k0 squared plus a squared, and then this will be e to the power of I e to the power minus I k0 r minus e to the power of I k0 r. Yes. So now we have this integral. Now what do we do next? We realize that this we can actually do a change of variables. So this actually can split up into two integrals. So imagine we first do the integral separately. So we do d k0 over k0 squared plus a squared e to the power minus I k0 r, and then we minus this other integral k0 prime. I'll write k0 prime for convenience. So k0 prime over k0 prime squared plus a squared e to the power of I k0 prime r. Then we oops, I seem to have run out of space. Okay, but the next step is to use you do a change of variables. So you do for this k0, you set k0 equals to k0 minus k0 prime. So then what you get in the end is you get that this is then you realize that you switch the minus and plus infinity to become minus infinity to 0, and you get integral from minus infinity to infinity k0 e to the power minus I k0 r over k0 squared over plus a squared dk0. And so this integral, we are very close to the final answer already. This integral can be done using contour integration. Okay, so I'll go ahead and jump over to the next piece of next blackboard. Okay, so once again, reminder, our goal is to show that g of r, so far all the steps we have done, we have shown it equals to I over 2 pi squared r integral from minus infinity to infinity of k0 e to the power minus I k0 r over k0 squared plus a squared dk naught. We want to show that this is equals, we need to show, I'll put a question mark here because we haven't showed it. I want to show that this is equals to e to the power minus ar over 4 pi r. And reminder that r equals to magnitude of the r vector. Okay, so how do you show this? We can show this using contour integration. So what do you realize? So let's term this particular term fk naught. Okay, so we realize that let's sketch the poles of fk naught. So we have the poles are the one satisfying the one where denominator equals to 0. So we have k naught equals to plus ia, and we have k naught equals to minus ia. So when we integrate from minus infinity to infinity, we have these two poles, and we can use them to advantage by closing the contour. So how do we evaluate the integral? So let's see. So we see first thing that the numerator is e to the power of minus I k naught r. So that spells that hints at us that we should use Jordan's lemma. So we want it to be this exponent to be negative, or rather, yeah, we want the whole thing to be positive. So we want k naught to be negative, or rather the imaginary component of k naught. So what do we do? In order to use Jordan's lemma in this situation, we need to close the contour in the negative half, the lower half plane of the complex plane. So we close the contour like this, and so we have that g of r equals to, now we close this contour, then this curved part is the integral of this curved part, this semicircular arc, is simply equals to 0. Then we have the so what this leads to is, because the integral, closed loop integral, equals to integral of minus infinity to infinity plus this arc, then, and we know that this one the closed loop integral can be, you can use the residues, so it's minus 2 pi I times the residues, and then this one disappears. So we know that this integral that we're interested in is just minus 2 pi I times the residues. So it's minus 2 pi I. Okay, we forgot the few factors in front. I over 2 pi squared r, then we have minus 2 pi I. Okay, let me just clear this over here. So then we have the residue of f of k naught at k naught equals to minus ia. So if we have these residues, how do you complete the residue of f k naught? So let's write f k naught in expanding the denominator. We have k naught plus ia and k naught minus ia. So the residue of f of k naught at k naught equals to minus ia is simply k naught plus ia times f of k naught, the whole thing evaluated at k naught equals to minus ia. So it cancels out, so this is simply k naught e to the power minus I k naught r over k naught minus ia evaluated at k naught equals to minus ia. And this in turn is equals to minus ia e to the power of minus ar over 2 minus 2 ia, and this is equals to e to the power minus ar over 2. Getting very close there. So what do we see? So from here we have this equality sign. Let's go over here. This equals to, now we can cancel one factor of 2 pi, so we have minus I over 2 pi r, and then we have e to the power of we have we have I times minus I gives us 1, then 2 pi, and 2 pi squared gives us 2 pi, and r gives us r, and this is just minus EAR over 2. So there we go, we have e to the power minus AR over 4 pi r. So what we have shown in this video is we have shown that number one, to find the Green's function. So what have we shown? Our original goal was to find the Green's function of this, and we have showed that if we want Green's function of this particular function, so step 1 was this, to find the Green's function of this. So step 2 was to expand g of r in terms of the Fourier expansion, Fourier transform g of k e to the power of ik dot r. Then step 3 was to expand minus this in terms of the right hand side, in terms of the Fourier expansion. Okay, so this is equals, so then we have the fourth step, which is the left hand side equals to this, which equals to Fourier transform this g of k, that was then minus k squared plus a squared, or sorry, minus a squared e to the power of ik dot r. Then we so this, the number 3 was equals to the right hand side. So then number 5 we compare step 3 and 4. Then we obtain that g of k equals to 1 over k squared plus a squared, right? Yeah. So then the next step was to, step 6 was to calculate. So now we take 5 and sub into step 2, and so that gives us g of r equals to integral of d3k over 2 pi cube and 1, so then that gives us e to the power of ik dot r over k squared plus a squared. Then step 7 was to express k in terms of the spherical coordinates. Okay, then we can use this to compute we can use this to compute 2 of the integrals rather easily, and the third one using contour integral. So in the end, use contour integral to get g of r equals to e to the power of minus AR over 4 pi r, where r equals to magnitude of the r vector, and hence we have solved our original goal of finding Green's function of this differential operator. And then once again, if you want to link back to this particular passage, we simply substitute a equals to 0, then we get, so if we set equals to 0, then g of r equals to 1 over 4 pi r, and that is in fact the Green's functions that we are desiring. So with that, I've come to the end of the video. I hope you have enjoyed, and if you do so, please leave a like and subscribe. Have a nice day. Bye.